practice 1.7. I'm going to go through and solve these for you to kind of give you a hand to make sure that what you're doing is good, and especially with the graphing calculator, inputting some of this in. So let's get started. It says identify the parent function for g from its function rule, then graph g on your calculator and describe the transformation. So remember, we have those four, let me just kind of highlight those really quick. We have the four parent functions, kind of like the OGs, if you will, for each family. So you have y equals x, which is just a line, that's linear, all right? And then you have y equals x squared, which is a quadratic, all right? And so that's the quad. And then you have y equals x to the third, which is something that looks like that, and that's a cubic. And then the last one that we did was y equals the square root of x, which kind of just looked like that, and that is the square root function. And one thing that you want to kind of understand with these are that they all go through the origin. So every single one of these, the vertex of my quadratic there is at the origin. This person crosses right through there. This person crosses right through there. So they're all kind of centered at the origin. And if you look at the power, the biggest power tells you which one it is. So if you're first degree, you're linear, second quadratic. So I think I have mentioned in the notes that if you have something like, 5x plus 2x squared plus x to the third, and you're like, well, hey, maybe it's linear because it has an x in it. Or maybe it's quadratic. Or maybe it's a cubic. It's always by the largest power. So this one is going to be dominated by that term. So this would be a cubic, some version of a cubic function. So that's just a little kind of heads up. All right, so let's get rolling. So this first one, g of x equals negative x squared. Well, since it's a squared, this is going to be in the quadratic family. So it is a quadratic. And I'm going to pull up my graphing calculator here. So let me pull up the graphing calculator. And shrink him down a little bit. And get this in the screen. Hopefully don't want to close that out. Just kind of get it to where it fits up here. Hopefully you can see all the keys. So y equals negative x squared. I'm going to go to my y equals menu, type in the negative key, which it looks like it's just off this screen a little bit. Oh, sorry, trying to make it fit in the video so that everybody can kind of see what's going on. All right, I guess you can see that on there. So y equals negative x squared. And I lock it in, hit enter. I'm going to go to my table, second table. And I want to see a few negative values, so I'm going to toggle up a little bit. So here we go. I'm going to start putting these points in here. So I have negative 2, comma 4. So left 2, down 4, right there. And I have negative 1, 1. Then I have 0, 0. Then we have 1, negative 1. 2, negative 4. And I could do some more points, but I think that gives me a pretty good picture of what's going on. So it's definitely a quadratic. The problem is it's facing the opposite direction. The standard one was up here somewhere. This is what the OG, this is what y equals x squared looks like. So it looks like it flipped down. So I'm going to say that there was definitely a reflection across the x-axis. So the transformation is reflection across the x-axis. And there was a teacher made where it kind of graded it for you, and I believe I made this one a drop-down menu. So you had some choices to pick from. Also, if you compare his table, negative 2, negative 1, 0, 1, 2, and you got 0, 1, 4, 1, 4. If you compare that table with this blue table here, and you go through and you analyze them, -2, -1, 0, 1, 2, and you try to match them up, you will notice that everything pretty much is the same with one exception, and that is all the y's are opposite. So you had these y's, now we have negative y. So that's also a tip-off to show you that if the x's stay the same and the y's just change value, opposite y's, then there's a reflection going on there. All right, let's try the next one. So I'm going to kind of move this calculator off to this side. And so we have square root of x minus 4. Well, I guess that kind of gives us the, kind of tells me what it is. It's a square root function. And I really don't know what it looks like until I kind of make a table. Now I could graph it. Sometimes you can't see as well on the graph, but I could graph it. And I could go in here and I'm going to go to y equals. And I'm going to clear that out. And I'm going to hit second x squared. That's a square root function. And then I put x minus 4. And my square root bar is still going, so I'm okay. I'm going to arrow out of that and hit enter. And now let's just graph it. Let's see what it looks like. So when I hit graph, whoop, so I notice it does kind of look like the normal square root function. So if I go and I put the square root function in there, the real square root function, I'll put it kind of light. It goes through 0, 0, square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. So this is the square root function. All right? We didn't have negatives because you can't really have negative square roots. And I'm just going to put the points that are the perfect squares because it makes it easier. The other x's are weird decimals. And then these are the y's. So these are x's, these are y's. Now that's from the parent. If I do the blue function, which is, you know, this new one here, well, I notice that it's over here, it crosses right there, and it's kind of hard to tell from my picture. I mean, you might be able to read that there, but that grid's kind of small. So one thing, I think it's easier to just use the table. So I'm going to go here to second graph, which gives me the table. And notice all those errors. I have all these errors, meaning, hey, there's no graph there. And really, I don't start getting anything until 4. So when I go through and I start putting some of these values in here, you know, at 4, I'm at 0. And then at 8, I'm at 2. That's like the next spot where I'm at, kind of a normal number. And I could keep on going and keep on going and keep on going, but basically, this thing just kind of shifts over 4 to the right. And I could look down further. I could kind of look at more numbers. But this one was just moved right 4 units. So that would be my transformation. We had a translation 4 to the right. Just kind of moved it over. All right, let's go down and look at the next couple. So y equals 2x. I'm going to just use the table on this one because this one's a little bit easier. So the only power is a power of 1. So I know it's going to be linear. So this is definitely a linear function. And the parent is y equals x. So the parent function, when I make my table, they have to match up. -2 is -2. -1 is -1. 0, 0, 1, 1, 2, 2. That's the parent function. Well, this function, g, which I'm going to put in blue, and let me graph that. It kind of goes, this is the parent function. So that's the line y equals x. Well, in blue, I'm going to do this y equals 2x. So if I plug these same values in there for y equals 2x, when x is -2, I get -4. When x is -1, I get that. 0, 2, 4. You'll notice that the y's, something happened to the y's. You know, this value got multiplied by 2, got times by 2. This value got times by 2. This value didn't change, but when you times 0 by 2, it stays 0. Times by 2 times by 2. So this transformation, all the y's were multiplied by 2. So the actual transformation is when you multiply y's by 2, you stretch them away from the x-axis. So technically this is a vertical stretch. I'm pulling the y's vertically away from the x-axis. So like when I graph this new one, you know, instead of 2 being at 2, 2 is now at 4, you know, from this point. And all of these points, they're all twice the distance away from the x-axis. If I were to keep this table going, 5 would have given me 10, which would have been up here, and you'll notice that that's double the distance. This distance was the original function. We're now double that distance away. So this would be a vertical stretch by a factor of 2. Last one over here. This one is the cubic function because we're to the third power. So this is a cubic. I would probably put this one in the graphing calculator. So let's just do that really fast. Pull this up. Go to the graphing calculator. Y equals, clear that out. Parenthesis, variable, minus 3, parenthesis, second power. Enter to lock it in. And now let's go to our graph. No, I did second power. I screwed up. I'm like, wait a minute, that doesn't look like a cubic. So I got to go back and I got to edit this. Go over here to the 2 and say, delete you, make you a 3. Now we're in business. Enter, lock it in. Second. So there's my table if I want it. I actually just want my graph. So it looks like, you know, the normal function. So first of all, I want to kind of see what the cubic function looks like. The cubic function comes up, cuts right through there, and goes back up again. And some key points that it goes through is it goes through 1, 1, and then it also goes through 2, 8, and 0, 0. And the negatives, it goes through -1, -1, and -2, -8. Those are some values in the table. Well, when I look at this one, getting rid of all this craziness over here. When I look at this one and I go to my table, you're going to notice some values here. Second table. Well, some values match up, but they're in different places now. So check this out. So now I'm at 3, 0 instead of 0, 0. And now I'm at over 4, up 1. I'm at over 2, down 1. So it's kind of got this same little bit. It's just happening over here. So it looks like this function got translated. So translated 3 to the right. It's the normal y equals x cubed, but it got moved 3 to the right. Number 5, graph the data from the table, identify the parent function, and then the transformation. So instead of giving us an equation, they actually are just giving us a table, which is not quite as good, but it's still pretty good. So let's put these points on here. So my first order pair is x is -4, y is 8. So I got -4 up 8. My next order pair there is -2, +2. So -2, +2, left 2 up 2. Then we have 0, 0, which all of our parent functions go through 0, 0. Then I have 2, 2, 2, 2, which is over 2 up 2, and 4, 8. All right, so 4, 8. So this to me, right away, is kind of looking like, it's looking like a quadratic. Because a quadratic kind of has this bowl shape, you know, where it comes down, bottoms out at the vertex, and then goes back up the other side. So I'm going to say that this is a quadratic. And now the transformation might be a little bit tough because you might say, well, it kind of looks the exact same to me. So there's a couple different things you could do. You could graph the parent function on here, like by hand. And so maybe I'll just quickly do it because I know the numbers pretty fast. So there's the parent function. He's the OG, he's the original quadratic. When you graph him out, you get, when you put -2 in, -2 times itself is 4. So left 2, up 4. And when you put -1 in, you get +1. So right there. When you put 0 in, you get 0. So that actually stayed the same. When you put 1 in, you get 1. So 1, 1. And then when you put 2 in, you get 4. And if I wanted to go even a little bit further, I could put in 3. You know, and get 3 squared is 9. So go over 3. I could go all the way up here to 9. And -3 will also take me up here. So here's the original. This is the OG. That's y equals x squared. Well, when I look at what happened to the blue one, the blue was the transformation. It looks like it did not move right or left. And how I know that is because the vertex stayed in the same spot. So it did not move right or left. I can rule that out. It did not move up or down. So basically what happened is this thing got kind of stretched or got kind of moved. And it might be easiest if I kind of match up some pairs. I try to match up what's going on. So if I put this table over here, I'm like, all right, let's line him up. Well, the numbers that line up, I have a -2, and I have a where I have a 0, then I have a +2. So this was 2, this was 0, this was 2. So when I'm kind of analyzing and saying, well, you know, what exactly happened here? It looks like what happened was my y's, these y's in this column are in half. So they got multiplied by a half. So my y's got multiplied by 1/2. So when y's got multiplied by half, that's a compression. That means that the y's shrank. You know, so this was an original y. The new y is now half the distance to that x-axis. So I'm kind of visualizing this x-axis here. And the points all came down in this direction. That point went down. This point went down. This point went down. This point went down. So this would be vertical compression. Vertical compression by 1/2. So everything got smashed or got flattened out by a half. Kind of got wider. So that one's kind of tough. I think these transformations can be a little bit tricky, a little bit difficult. I want to show you another way to not identify transformations, but to look at a table and find the parent function. So I think I showed you guys how to do this in class, but if you were absent or if maybe you were working on something else, you might have missed it. But there's another way to analyze a table is to look at the differences in the table. And I'm going to walk through this first one and then I'll do the other ones as well. So label this column right here. This is called the first difference. Actually, I'm going to give myself a little more room. So this is the first difference. Kind of put a line down. This is the second difference. Put a line down. And then we'll never go past the third difference, at least in this chapter we won't. And let's kind of look and see what's going on. So what I mean by differences are the differences are the changes in the y values. So when I look at 3 take away 1, there's a difference there of 2. But when I look at from 9 to 3, 9 take away 3, that's a difference of 6. And when I do 19 subtract 9, that's a difference of 10. And let me kind of space this out because that 6 I want in the middle of those two numbers. And then the difference between 33 and 19 is 14. And then the difference between 51 and 33 is 18. So I know I'm not finished because the differences are changing, like they're not the same. So it's definitely, the first difference didn't yield anything really good yet. So now I'm going to play that same game again. The second row of differences, a column I should say, is 4. Ooh, subtract this, I get 4. Subtract that, I get 4. Subtract that, I get 4. I've now found they all match up. So what that tells me, because it's the second difference, all right, I want you to think of this as like powers. The second power means that this table is going to be a quadratic. So I can tell you that number 6 is definitely going to be a quadratic function because the differences in the y values didn't become the same. They weren't constant until the second difference. Now let's compare that with number 7. So I'm going to make this one go a little bit quicker because I was just explaining in that last one. So we have first difference, second difference, third difference. Well, in this first one, I have 4, 4, 4, 4, 4. Oh, problem's over. If you're the first difference, that associates with a power of 1, so kind of think like x to the first. This is linear. So I know that this set of numbers is going to form a straight line because it has constant change. And actually, just kind of giving you a little extra insight, it's the slope. This line's going to have a slope of 4. It's changing by 4 every single time x changes by 1. This line didn't happen until the second one. So now we go to number 8, the last problem here. And you probably expect, well, if we had the first one went to the second, that one went to the first, you know, I'm a math person. I'm always kind of making predictions and doing patterns. I would bet this one's going to go to the third, and I think you'd be right. So I look at the difference. I got to be careful with negatives. I got to go backwards there. So -3 subtract -4. Well, that's really 1. 4 take away a -3. Well, that's 7. Now it's a little easier. 23 take away 4. 60 take away 23. What's that? 37. And then 121 take away 60 is 61. So nowhere near close yet. So let's keep going. Second difference, 7 take away 1 is 6. 19 take away 7 is 12. 37 take away 19, that'd be 18. And that one would be 24, it looks like. So nothing quite yet. Third column, when I do the difference, I get 6, 6. Ooh, 6, finally. I have a common difference in row 3. So when you have a common difference like that in the third one, kind of think of the third power. I know that this table represents a cubic function. So sometimes it might be faster or easier. Like this would be really hard to graph. That would have to be a big graph to do 5, 121. And then it might be tough to know, is it x to the third? Is it x to the fifth? Like a graph might not really tell you that, where doing this analysis locks it right in. You know it's got to be a cubic. So hopefully that helps you out. That's kind of an advanced technique that normally in a regular algebra class, advanced algebra, you probably wouldn't do that.